Now to the final presentation from Fuller. I'm very pleased to welcome Ahmed Seaf, a process specialist at Fuller with over 17 years experience in the cement and minerals industry. He's worked internationally across diverse cultures, supporting commissioning, optimization, and aftermarket services for cement plants, consistently delivering high productivity results through strong technical expertise and teamwork. Ahmed, welcome. If you'd like to share your slides with us and get started with this
thank you.
last presentation. Okay, they're just coming up now. I'll let you know when they're visible. And that's it. Okay, over to you, Ahmed.
Thanks, Thomas, for the introduction, and good morning, good afternoon, or good evening to everyone, depending on where you are joining from. First, I would like to thank Cemtech for organizing this webinar and for bringing the industry together. My presentation will be around one of the most important questions in cement industry today. The question is how to reduce clinker while keeping production stable and commercially reliable. My name is Ahmed Seaf. I work with Fuller Technologies for the last 12 years, with more than 18 years of experience in the cement industry. Fuller Technologies has a long history in the cement industry, from supplying complete pyro system and grinding circuits to plant optimization, digital control, and service support. The main message today is simple. Higher SCM substitution is not only a chemistry challenge. At industrial scale, it becomes an engineering challenge. The real question is not only whether we can make it low clinker cement, the real question is whether we can make it sustainable, profitable, and at scale. In the next 15 to 20 minutes, I will walk you through a practical engineering view for higher SCM substitution. We will start with the main question: why are 50% clinker cements still not common in stable large-scale production? From there, we will look at the SCM landscape. Then we will compare grinding strategies, as well as we discuss where ball mills or VRM system fits. The focus then will shift to variability, because at high SCM levels, stability depends on how quickly the system can react to material change. Then we will discuss together what can be improved using the existing assets before moving to major capital investment. Finally, I will close with a practical pathway to reach 40 to 50% clinker in a controlled, validated, and scalable way. Let's start with the question why the answer is no long chemistry alone. The industry has already moved beyond several traditional barriers. Standards are such as the EN 197 5 and the ASTM 595 are opening more space for blended and multi-component cement. The market demand is also moving. Customers are asking for low carbon products. The SCM's options also exist in many regions, such as the fly ash, the slag, the calcined clay, limestone, and natural pozzolans. Digital tools also are becoming more stronger, from process control to real-time optimization. So the question now becomes very clear. If the standards and the market are moving, the material are available, and the tools are improving, why still 50% clinker cements is rare in stable large-scale production? The answer is the engineering. So for many producers, the question is no longer, can we make low clinker cement? In many cases, the answer simply is yes. The harder question is, can we make it constantly, profitably, and in industrial scale? That is where most plants face the same three walls. The first wall is the grinding system. Many circuits were designed around clinker-rich cement, not high SCM variability. The second wall is the process control. When moisture, loss of ignition, and fineness or reactivity changes, the plant often reacts too slowly. The third wall is the flow sheet logic. Many plants still operate with layout and storage concepts and the quality loops inherited from a high clinker world. So the barrier is not only whether the material works, The barrier is whether the full plant system can keep quality stable while the material stream is changing. So before we talking about the grinding technology itself, we need to look at the material themselves. A higher SCM substitution doesn't create one material problem, it creates a moving material system problem. So there is no single SCM future for the whole industry. Fly ash, slag, calcined clay, limestone, and natural pozzolans can all support clinker reduction, but each one brings a different engineering challenge. For example, fly ash can vary in loss of ignition, carbon content, moisture and fineness, and also the source consistency. For the slag performance, it depends on reactivity, on the glass content of the slag, and the chemistry and the supply reliability. Calcined clay has a strong potential, but it depends on the kaolinite content, calcination quality, moisture, and water demand. Limestone is widely available, but purity, hardness, moisture, and BSD can strongly affect the final cement performance. Finally, natural pozzolans can be very valuable locally, but they are highly source specific. So the mill no longer processing a fixed recipe. At high SCM substitution, it is managing a moving material stream. So the next issue is what actually reached the mill. On the material certificate, the material may meet the specification. Loss of ignition, moisture, reactivity, fineness, all within limits. But in operation, in reality, the mill doesn't grind the certificate. It grinds material arriving at the feeder. So between dispatches and dosing, the material can change. Loss of ignition can shift with a source blending or with unburned carbon content, and the moisture can increase during the transport or storage. The reactivity can change with slag, clay calcination, or pozzolan mineralogy. The BSD also is very important as it can affect the strength or the separator loading or water and sulfate demand. Even handling and storage matters. Two SCM deliveries can meet the same specification but behave completely differently in the silo or in the dosing system or in the mill. So the real question is whether the plant can detect and absorb and correct that variability during continuous production. Now let's turn this into a practical stress test. Imagine your plant is being asked to produce cement at 50% clinker starting tomorrow. No new permits, no new mills, no new customer, just the existing plant and the existing operating team. What break first? In most plants, the pressure appears first in the grinding system. So the SCMs must be fine enough to contribute to the strength and reactivity. At the same time, the clinker should be not overground because that can waste energy and increase water demand. The sulfate balance also become more sensitive, and the whole system must stay inside a tight quality envelope. So 50% clinker is not just a formulation target, it's a full system capability test, and it tests grinding, drying, classification, blending, sulfate control, quality control speed, and process response. With the material challenge in mind, the grinding question becomes more focused. The issue is not simply a ball mill or VRM or hybrid circuit. The issue is what the cement needs from the grinding system. The key point here is the clinker and the SCMs, that the clinker and the SCMs don't need the same BSD target. Clinker needs an optimized BSD to protect strength without unnecessary overgrinding. SCMs often need finer or more controlled grinding to unlock reactivity and improve particle packing. When everything is ground together, the plant may compromise both sides. Softer material can be overgrind and increase water demand, while harder clinker may remain underground. That's why separate grinding, or at least better controlled grinding, becomes important at 40 or 50% clinker. The objective is not just to chase one plain number. The objective is to control the right BSD for each component. Once we understand the BSD principle, the next question is how to grind the material. Co-grinding is simpler route. It usually means lower capex, fewer equipment, and simple process flow. For moderate substitution with a stable material, it can be a practical solution. But the limitation is that the all material are forced into one grinding target. Softer SCCMs may overground. At the same time, harder clinker may remain underground. Separate grinding gives more control. Each component can reach its own BSD target, so SCCMs can be activated without unnecessary clinker overgrinding. So that can improve water demand, early strength, and higher substitution ceiling. So the decision is not simple versus complex. The decision is how much control is required to reach the clinker target and the clinker factor in stable production. At this stage, the investment question is not simply ball mill versus VRM. A ball mill is a proven and familiar and often has a lower initial capital requirement. But at higher SCM, the limits can appear in drying capacity, PSD control, and the separator response. A VRM, including the OK mills, can offer lower specific power consumption, stronger drying capacity, and better separator response and better PSD control. But the real point is not energy saving alone. The investment case should be built on a stable clinker reduction. So before committing capital, the first step is to audit the real constraints and understand what the system actually needs. Once the grinding strategy is clear, the next challenge is speed. At a high SCM substitution, the plant must respond in minutes, not in hours. Here is a practical reality. Imagine a Tuesday normal production morning, an SCM delivery arrives from a different source than last week. The loss of ignition is higher than expected. Moisture is also higher because of the transport and the weather, but the mill still running on yesterday's settings. And because of the delay in the quality response, the first lab report only comes back at 3 hours later. By the time operator adjusts manually and change the production and the production supplies, the plant may have already have many hours of exposure. During that time, the plant may be producing cement with shifted blend, changed water demand, changed sulfate response, or changed strength development. That's why variability is very dangerous at high SCM substitution. It is not an exceptional event, it's a normal production day. The same Tuesday morning would look very different when response loop is faster. Without advanced process control, the plant depends mainly on the lab feedback and manual correction, very long exposure window. With ECS or process expert and advanced process control, the target is to reduce that exposure window from hours to minutes. The system can detect the shift earlier and adjust the blend, change the operating target, recalculate quality related setting, and increase the quality control response. The value of control is not only automation for its own sake, the value is the response time. At high SCM substitution, faster response can turn a bad production day into a manageable one. Before assuming the answer is a new mill, the existing circuit should be tested first. Many plants still have clinker reduction potential inside the current system. Clinker reduction is usually not one big move. It's a cumulative pathway where several smaller improvements can work together. For example, limestone filler combined with better PSD control may allow around 2 to 4 percentage point of clinker reduction. A separator or classifier upgrade can add another 3 to 5 percentage point if the classification is the real bottleneck. Sulfate tuning and faster quality control may each support 1 to 2 percentage point. Moisture handling may unlock 1 to 3 percentage point, especially with wet SCCMs. Finally, SCCM blend optimization may add another 2 to 4 percentage point of clinker reduction. The point here is not to add this number blindly. The real value depends on the plant constraints, material quality, and market requirement. So in the working example here, moving a 2 million ton per annum plant from 72% clinker factor to 60% means about 240,000 tons per year less clinker and roughly 200,000 tons of CO2 avoided per year. The key message here is, sorry, the key message here, the key message here is that the existing asset should be audited before a major capex is justified. At this point, the question becomes a risk reduction. The plant needs a structured way to move from ambition to evidence and from evidence to action. A process audit should not be a report that sits on a shelf. It should deliver a prioritized capital decision list. The audit should identify the real constraints in the plant, the possible intervention, the clinker reduction potential, and the decision needed. If separator efficiency is below the design curve, the output may be a retrofit case. If moisture handling is limiting stability, the output may be storage, drying, or feed condition improvement. If the quality control cycle is too slow, the output may be faster lab automation or online signals. If advanced process control is underutilized, the output may be a process expert system retuned. And if the product approval pathway is the barrier, the output should be a standard review, concrete validation, and customer acceptance plan. The value of the audit is clarity. It tells the plant what to fix first, what to postpone, and what business case to take forward. The implementation sequence matters. The safest pathway is evidence first, one constraint at a time, then validation before scaling. This is the practical sequence I would recommend. Phase one is understand. Before spending capital, the plant needs to audit the grinding circuit, characterize the SCM source, and complete material testing where needed. Phase two is fix the bending constraints. Don't try to fix everything at once. Select one target, such as a separator performance or the advanced process control, or maybe the moisture control, and build the capital case with evidence. Phase 3 is scale. Once the system is stable, the blend strategy is valid, and advanced process control is tuned, then the plant can move step by step forward to the target clinker factor. The most common failure is skipping phase 1 and going directly to capital spend. The audit is not optional. So thank you for your attention, and I hope the main message is clear. The move toward 40 to 50% clinker is not only formulation or chemistry challenge, it's engineering challenge. Thank you again, and I'm happy to take your questions.
Ahmed, thank you very much for your presentation and a very clear route to SCM use and clinker reduction. It's quite an ambitious target, the 50% clinker reduction, but it's one that we can hopefully move towards. What are the best examples of clinker reduction that you've seen recently?
Yes, so recently we have the LC3, we have a clinker reduction up to 50% achieved by adding calcined clay. We have two projects, one of them in France and the other one in Ghana. And I think we achieved 50% clinker substitution by limestone and calcined clay. Also, we are doing a couple of R&D projects on limestone. We have done some tests achieving 30% substitution, limestone substitution. So it was a big number, and the result so far looks promising. And hopefully, maybe in the next webinar, we can share the results of this R&D project.
Okay, and that's limestone and just with clinker or with other additives or combinations?
Yeah, that's only limestone, clinker, and gypsum.
Okay, and what kind of role are you seeing for additives in this? Obviously, the grinding is the focus, but additives can play quite a big role, I believe.
Yeah, additives can play a big role because fine grinding and now is the development or the moving is going to separate grinding. And in separate grinding, we need to grind finer to have the strength. And one of the things that we have seen that the water demand is increased. So maybe the additives play a role to retard a little bit the water demand, or maybe also the setting time. So that's also we are now have an agreement with some concrete testing to do a concrete testing to test the water demand and see the additives impact on this.
Yeah. Is that especially the case for calcined clay cement?
Yeah, no, and we're doing that for the limestone R&D
Mm.
project, but also for the calcined clay, I believe the additives will play a vital role.
Yeah. In the US, where you're now based, what are the kind of main trends that you're seeing?
Yeah, the main trends now, as mentioned earlier, that most of the companies now is increasing the limestone dosage from 5 to almost 10% limestone in the same existing. But also, I have seen some customers they're trying to do the separate grinding, but as also mentioned that the layout constraints, because separate grinding you need to have two different units, and also the storage layout constraints. So there is a little bit slow in that regard, but I believe it's the future of the cement grinding is to do separate grinding.
And in the US, obviously for the cement producers, they want to control the products that they put out to the market, maybe reduce the clinker and take the benefits of reducing that clinker. But we see a lot of independent imports now. Importers are going into the grinding business so that they can maintain their control on the products. So it seems that this shift is actually having quite a profound effect on the market in the US.
Yes,
Um,
that's correct. Yes.
yeah. So does that suggests that actually people are wanting to really control their products more closely? Um, is that something that is going to be more prevalent going forward?
Yeah, I believe so, because I can see also many manufacturer now is controlling the products by the BST control. So now there are big shift from controlling the plane only by and going to the BST and the seeds. And this is, I think this is the new controlling of the products and the finance, or to have a better understanding of the performance with a high substitution of the SFCMs and the supplementary material.
Very good. Well, Ahmed, thank you very much. Thanks for
Thank
your
you.
comments.
Thank you so much.
That's all we have time for today. I think we've seen a fantastic range of technology, expertise, the grinding, the use of AI, the emphasis on audits and planning ahead, and to really strategize as grinding becomes more sophisticated and the materials that we use become more varied. So it's a very fascinating area, and we thank you for your contributions. We'll be sending the recording and the slides out by email by tomorrow. Do check them out if you want to follow up with any of the speakers. I'm sure they'll be more than delighted to respond to your queries. Thank you very much. We'll see you at the next Cemtech webinar next month, if not before, in Bangkok for Cemtech Asia. Thank you very much.